Hello everyone, here we are on the beach near Arisaig Lighthouse on quite a windy day, and in this section we can see that we have two very different rock types. If we look a little bit over there in the water, we see that the rocks are very dark, whereas here where I sit at the moment the rocks are much light and they kind of pinkish in color. So we see that there are two different types, and we're going to examine them in more details just to see what they are. We're going to start first with a lighter colored rock, and if we look on this outcrop, we see that the color is kind of pinkish, creamy, slightly different in different places. We also see that the rock is extremely hard. So it is very hard if I try to scratch it, and also to break it, it's very difficult. So it's very, very solid and very competent rock. So first we need to decide between our three main options, if the rock is sedimentary, igneous or metamorphic. And of course the hardness of this rock and the competence of this rock definitely say that this rock is not a sedimentary, so we can rule out this option right away. And we're left with two, whether it's igneous or whether it's metamorphic. So metamorphic rocks would show, most of them would show foliation, some kind of a planar or linear fabric that is developed by the minerals that grow and orient themselves during metamorphism under the regional stress in certain direction. We do see lots of linear features in this rock, but you see that they all banded and irregular, and if we look closer, there are no minerals like mica that would actually be responsible for any planar features. So this is not a foliated metamorphic rock like schist or slate. This is definitely something different. There are some non-foliated metamorphic rocks that could be marble, but this is clearly not marble because marble is made out of carbonates and this is very hard rock. Could be quartzite, could be amphibolite or greenstone. But amphibolite and greenstone are dark in color, so again not our option. So the only possibility would be quartzite. But quartzite is a very sugary rock with a sugary texture, with a small grains of compressed sand, what used to be a sandstone. And if we look closer, we don't see the sugary texture, we don't see kind of rounded quartz sand. Instead, we see lots of other features. So this is definitely not a quartzite, and this is something different. Let's look in more details what actually we see in this rock. So we already saw these bands. They're very wavy. They go in all the different directions, and sometimes they go together, sometimes they go apart, so there is no regularity. It's definitely not a bedding, it's not folding, it's something again quite different. So we see these bands. We also see that the rock is very, very fine grained, but it does have a little bit larger crystals, rare crystals here and there, and it has this system of fractures filled with quartz. So these features here, this is a flow bending, which is very typical for very viscous lavas. So when this viscous lava is flowing, they stretch and they form this flow bending, and that's why it has all this kind of rounded but irregular shape, and basically it captures the way the lava was flowing. Also, all these regular oriented veins, they may be just simply the result of fracturing in the cooling lava flow and escape of the gases, because we have lots of volatiles trying to escape from crystallizing magma. Here we are very close to the water line, so the ocean is right here, and as a result there is quite a bit of weathering by the waves, especially during the storm happening to the outcrop right here. So we can see the flow bending exposed even further by this weathering. But we also see that in addition to the flow bending, we also see many fragments. Like this area over here is full of fragments with a flow bending. There is a small fragment over here. There are some larger fragments, this one here. There are smaller one here. So this is all fragments of the same rock. We see the same flow bending, cemented by, again, the same rock, but with less of the flow bending. And this is because if we think about the very hot lava, 700–800 degrees, moving on the surface in contact with the air, which is of course much cooler, then the top of the lava flow is going to quench very quickly and to develop this crust, which is already solid, whereas lava inside the flow is still trying to move and to push this crust. So the crust as a result can get broken, and the pieces of the crust get remixed back in the lava flow. And that's what we see here, all of these fragments. There is also a very nice fragment on that side over here. And these tell us that right now we are somewhere very close to the front of this lava flow. We don't see the full extension. Also, if we look on that part of the outcrop, again we see all of these parallel veins. This may be related to metamorphism, but it could be simply related to escape of the volcanic gases during the solidification of this lava flow after it was deposited. So let's sum up what we see here and what we learned about this rock. So we decided that this rock is not sedimentary, it's too hard, no way. We decided that it's not a metamorphic rock because it's not one of foliated metamorphic rocks, and it's not one of non-foliated metamorphic rocks either, if we compare. Instead, what we see these wonderful flow features that tell us that this rock was a lava, which means that this was igneous volcanic rock that was flowing on the surface. Now, the next question is, what is this rock? How should we call it? So the rock is volcanic, and the color of the rock can tell us a lot about the composition. So this rock is very, very light, and also the way it's very hard to break, it tells us that this rock is very silica rich. So it's light color, very hard to break. If we look in the diagram, volcanic rock, which is very silica rich, which is light colored, it's a rhyolite. So, and rhyolite is very typical to have flow bending in rhyolite, so this also fits. So we can pretty much decide that this rock is a rhyolite, so it's a volcanic rock, very felsic, that was erupted on the surface as a lava and solidified to form this outcrop. So we saw flow bending, we saw pieces of broken crust, and we also saw fractures filled with quartz that resulted from escape of the volatiles from the lava during the crystallization. Let's now move and check the dark rock. Now we move to the second rock. Remember the dark rock that we saw initially? So this is this dark rock. Once again, it's very fine-grained, except for these white blobs that we'll discuss in a second. So the matrix of this rock is very fine-grained. It also very hard, but it's actually easier to scratch than the first pink rock, and it's also very solid. So very competent rock. That tell us that it's not a sedimentary rock again, so we can rule out the sedimentary option right away. And again, we have two other options, metamorphic and igneous. So with the metamorphic rock, we see absolutely no foliation or any planar or linear features. So it's not one of the foliated metamorphic rocks, such as schist and slate and so on. The non-foliated metamorphic rock, it's not marble or quartzite because it's very dark. It could be greenstone or amphibolite by the color. And actually this rock is about 460 million years old. It was formed as a part of Gondwana. So it may be metamorphosed to some extent now, and most likely it is. But what we're interested is what this rock originally was. Whether this rock was igneous, and we can look on other features that we see here. So we see these veins, of course, clearly cutting through the rock. So this, if we scratch it, it's actually, the white material is quite soft. So it's not quartz, it's a calcite. And if we take a closer look on the veins, we see all of this green material here, kind of the bright green color of epidote and the darker green color of chlorite and serpentine. This again points us that it was some kind of mafic material here with quite a bit of calcium. So, but we can also see that all of these veins, of course, are secondary and probably formed during this metamorphism. But what we also see in this outcrop, we see all of these white blobs everywhere around this rock. And we see that the shape of these blobs, this is definitely not crystals, they're very irregular. Sometimes they're more rounded, sometimes they kind of rounded irregular. So these blobs are vesicles that once were empty, existed in this rock, and now they filled with the different secondary minerals. So these vesicles only can be present again in lavas because they form when the volatiles exhale from the lava and these bubbles are trying to escape. And the vesicles filled with the secondary materials called amygdaloids. So this is amygdaloids, and the presence of these vesicles clearly tell us that this is again a lava, it's a volcanic rock. Now, what is the composition of this volcanic rock? It is dark, it is not as hard as the first one, so it has less silica and dark color, and the vesicles, these all very characteristic features of basalt. And vesicles are very important because even if your basalt is very metamorphosed and you see no primary minerals left in this basalt, this vesicular texture or amygdaloidal texture preserved for a very long time during metamorphism and can tell you that this, once upon a time, this used to be a basalt. Let's look on the distribution of vesicles on these outcrops, because you see that it's not uniform. For example, here on this cliff where I'm standing, if I look closer to the water, there are almost no vesicles. There are some very rare few vesicles here and there. There are some structures with a little bit more vesicles, but most of it is vesicle-free. Whereas as I move further from the water, I start to see more and more vesicles. And closer to this part, where the cliff is broken, there are lots of vesicles, tons of vesicles here. Why is it? If we think about the lava flow, flowing on the surface, vesicles clearly much less dense than the lava. So as soon as these vesicles form, as soon as volatiles exhale from the melt, these bubbles are trying to escape. It's like your bubbles in a Canada Dry, the CO2 bubbles are trying to escape from the liquid. So it's exactly the same here, but of course, unlike Canada Dry, the basalt is much more viscous, so it's not that easy actually to escape through it. So that's why they get trapped, but they still try to make it to the surface. So what we see in the lava flows, that the top part, typically where the vesicles are sitting. Why it is important? Because now we can see that we're looking on one single lava flow. This was one lava flow, and we can also say that this was the bottom and this was the top. The rocks are very tilted here, so this is a good indication for us of where we are in the stratigraphy. Why it is also important? Because these lava flows with the vesicular tops only form when basalt is erupted on the surface, where we have subaerial eruption. Because when basalt erupts in the sea, in the water, then it develops pilolavas, and this is completely different textures and structures that we would see. So here we're looking on the top of one lava flow and the bottom of the next younger lava flow. And in between the two lava flows, we see this brown material, which we also see that it's much softer because this is where the weathering happened, and so this material was weathered. This is a paleosol, so this is the material that formed during the weathering of this older lava flow before the next igneous event deposited the next lava flow. So this is the paleosol trapped in between and partially cooked by the next lava flow. So we see lots of vesicles in the top of one lava flow, and we see no vesicles in the bottom of the next lava flow. And we can also see that this lava flow continues maybe for at least 10 meters because we don't see again vesicles through this whole cliff. So let's zoom up what we saw on this outcrop. We had these two different rock types. We had the pink one, the rhyolite, and we ignore these construction boulders that exactly cover the contact between the rocks. But we look on the basalt. So we have the dark basalt, we have the pink rhyolite. So what is similar? Both rocks are very fine-grained. Both rocks are very solid. But remember that when I was trying to crush and scratch rhyolite, it was harder, significantly harder than basalt. But basalt is still a very hard rock, of course, as you know. So basalt has less silica, rhyolite has more silica, and we can even feel it when we're trying to break it. And again, we use the color index that light colored rocks are typically felsic, dark colored rocks are typically mafic, very fine-grained, with the flow features in rhyolite, with the vesicles in the basalt. So this is igneous rock, which is a volcanic, because it was erupting on the surface and forming lava flows. So the lava flow of rhyolite, of course, was much more viscous than the lava flow of basalt. And we use pretty much the color to name the rock, basalt and rhyolite. And this is again supported by presence of vesicles that are very typical in basalt, and presence of flow features that are typical but not necessarily always present in rhyolite. Also, we remember that presence of these vesicular layers, the vesicular tops in the basalt, is an indication for us of the eruption conditions, that the eruption was subaerial. These basalts erupted not under the water, not on the bottom of the ocean, but on the surface.